But can you see the boat? Do you see? Can you hear me? Do you hear me?
Да.
Okay. Do you see the boat? Can you see?
Да.
Okay. Today begin with example of investigation of the function. Write down example. Investigate the function y is x over 1 plus x squared. The first, the domain of the function is the interval from minus infinity to plus infinity. It will straightway be noted that for x is less than 0, we have y is less than 0, and for x is greater than 0, we have y is greater than 0. The second, the function is everywhere continuous. The third, test the function for maximum and minimum. From the equation y prime equals 1 minus x squared over 1 plus x squared equals 0, find the critical points. X first is minus 1 and x second is 1. Investigate the character of the critical points. For x first is less than minus 1, we have y prime is less than 0. For x is greater than minus 1, we have y prime is greater than 0. Hence, at x is minus 1, the function has a minimum. And minimum sign of our function y equals y at the point x is minus 1 or minus 1. It is don't minus 1 over 2. Yes. For x is less than 1, we have y prime is greater than 0. For x is greater than 1, we have y prime is less than 0. From this, at x is 1, the function has a maximum. And maximum sign is 1 over 2. Okay. The fourth. Determine the domain of increase and decrease of the function. For minus infinity to minus 1, we have y prime is less than 0. The function decrease. For x from minus 1 to 1, y prime is greater than 0. Our function increase. For x from 1 to plus infinity, the derivative of our function is less than 0. It means our function decreases. Then, fifth, determine the domain of convexity and concavity of the curve and the point of inflection. Calculate the second derivative that equal to 2x times x squared minus 3 over 1 plus x squared cubed. No, here squared, here cubed. Yes, equals 0. We get the critical points x first equals minus square root of 3, x second equals 0, and x third equals square root of 3. Investigating the second derivative as a function of x, we find that maybe I denote it on the minus line 0 square root of 3. For minus infinity to minus square root of 3, y2 prime is less than 0. The curve is convex. From minus 3 to 0, y2 prime is greater than 0. The curve is concave. From 0 to square root of 3, the second derivative will be less than 0. The curve is convex. And for square root of 3 to plus infinity, our second derivative is positive values and the curve is concave. Thus, the point with coordinates x is minus square root of 3, from this y is minus square root of 3 over 4, is a point of inflection. The point 0, 0 and square root of 3 over 4 are points of inflection to the way. The 6 determine the asymptotes of the curve. For x approaches plus infinity, y approaches 0. For x approaches minus infinity, y approaches 0. Consequently, the straight line y is 0 is the only inclined asymptote. The curve has no vertical asymptote because the function does not approach infinity for a single finite value of x. Plot the graph of this function using our calculation. From this, firstly, construct the table in which we have interval for x, then y, y prime, y2 prime. X we will have from minus infinity to minus square root of 3. then square root of 3, we minus square root of 3, we consider only 1. Then from minus square root of 3 to minus 1, then the point minus 1, then from minus 1 to 0, then the point 0, from 0 to 1, the point 1, from 1 to square root of 3, and from square root of 3 to plus infinity, last interval. In the first interval, our function decrease. If x is minus square root of 3, the sign of the function y equals minus square root of 3 over 4. On the interval from minus square root of 3 to minus 1, the derivative of the function is negative. It means our function decreases. At the point minus 1, the sign of our function equals minus 1 over 2. And the first derivative at this point equals 0. It is point of minimum. We find it, minimum. In the interval from minus 1 to 0, we have the positive first derivative and our function increase. At the point 0, the sign of our function equals 0. From 0 to 1, our function has a positive sign, our first derivative of function, and the function increase. At the point 1, we have the sign of function is 1 over 2. The derivative is 0 and it is point of maximum. From interval on the interval from 1 to square root of 3, we have negative derivative and our function decrease. At the point square root of 3, the sign of our function equals square root of 3 over 4. And after this point, the sign of the first derivative equals the negative number, and our function decreases. The second derivative. The second derivative equals 0. At the points minus square root of 3, 0, and square root of 3. All of these points are the point of inflection. Then the second derivative from minus infinity to minus square root of 3 has the negative sign. And our function in this case, our curve is convex. From minus square root of 3 to 0 positive, it is concave curve. From 0 to square root of 3, we have negative sign of our second derivative, and our function is convex. And after square root of 3, the second derivative is positive number and our function is concave. It is the table that we will use to construct our graph. Okay. And now let's plot the graph of this function. Y-axis, x-axis, zero, and here minus 1, minus 2, and this minus square root of 3, then 1, square root of 3, okay, xy. Then the critical points, it is minus square root of 3. In this point we have the sign minus square root of 3 over 4. Square root of 3 approximate equal to 1.7. 1.7 over 4 approximate equal to 0.4. 0.4. it is 1, it is 0.5, 0.4, maybe here minus 0.4, it is minus square root of 3 over 4, and here, yeah, square root of 3 over 4, okay, 1 over 2 minus 1 over 2, this, the point 1, 1 over 2 minus 1 minus 1 over 2, it is our critical points. Then here the point, the curve is convex, okay, minimum, then concave, convex, maximum, concave, convex. Don't forget about asymptote. It is our graph. Next example. Investigate the function y is cubed root of 2ax squared minus x cubed. Solution. The function is defined for all values of x. The second, the function is everywhere continuous. The third, test for maximum and minimum. From this, find y prime equals 4a minus 3x over 3 times cubed root of x times 2a minus x squared okay. There is a derivative variable except for the point x first is 0 and x second is to a. Investigate the limiting value of the derivative as x approaches minus and plus 0. Limit as x approaches minus 0 of 4a minus 3x over cubed root of x times cube root of 2a plus x squared equals minus infinity. And same limit as x approaches plus infinity. Plus 0, plus 0 of 4a minus 3x. Don't want to write down. Over this denominator, I try make it slowly. Okay, equals plus infinity. For x is less than 0, y prime is less than 0. And for x is greater than 0, y prime is greater than 0. Hence, at x is 0, the function has a minimum. The value of the function at this point is 0. Okay. Okay. At x is 2a, the derivative also approaches infinity. However, in this case, for all values of x close to 2a, both on the right and left of 2a, the derivative is negative. Therefore, at this point, the function has neither a maximum nor a minimum. And about the point x second is 2a, the function decreases. The tangent to the curve at this point is vertical. At x is 4a over 3. The derivative vanishes. Let us investigate the character of this critical point. Examining the expression of the first derivative, we note that for x is less than 4a over 3, y prime is greater than 0. And For x is greater than 4a over 3, y prime is less than 0. Thus at x is 4a over 3, the function has a maximum. And maximum sign it is 2 over 3 times a times cubed root of 4. Therefore, on the basis of the study, we get the domain of increase and decrease of the function. For minus infinity to 0, the function decreases. From 0 to 4a, maybe I write down this 4a over 3, the function increases. From 4a over 3 to plus infinity, the function decreases. The 5. Determine the domains of convexity and concavity of the curve and the point of inflection. The second derivative will be equal to minus 8a squared over 9x to the power of 4 over 3 times 2a minus x to the power of 5 over 3 does not vanish at a single point. Yet there are 2 points at which the second derivative is discontinuous. It is x first is 0 and x second is 2a. Let us investigate the sign of the second derivative near each of these points. For x is less than 0, we have y2 prime is less than 0 and the curve is convex up. For x is greater than 0, the second derivative will be less than 0 and the curve is convex up. Hence, the point with abscissa x is 0 is not a point of inflection. For x is less than 2a, the second derivative will be negative function and the curve is convex upward. And for x is greater to 2a, the second derivative is greater than 0 and the curve is convex down. Using this calculation, we must plot the table, but I now don't do it because I don't have a lot of time. you can make the table yourself. Now I just plot the asymptote. It is y is x plus 2a over 3. And our curve, it is maybe other color. It will be don't. Zero, zero. Then here for a over 3 point. This 2a and zero for a over 3 2a. This is graph of function y is cubed root of 2ax squared minus x cubed. The asymptote of this function we must determine using the formulas that I gave you in our last lecture. The straight line is minus x. Is an asymptote. This 6. Okay, now I will send to you these examples in the chat. Clean the board and we continue. Can you see the photo of our board? Do you see?
Yes.
Okay. Now I clean it and maybe we can continue. 1 minute, please. Okay. Our next subtitle, Investigating Curve Represented Parametrically. Investigating curve represented parametrically. Okay. Let a curve be given by the parametric equation x is phi of t and y is c of t. Formulas 1. In this case, the investigating and construction of the curve is carried out just as for the curve given by the equation y is f of x. Evaluate the derivative dx over dt equals phi prime of t and dy over dt equals c prime of t. Equations 2. For those points of the curve near which it is the graph of a certain function y is f of x, evaluate the derivative dy over dx equals c prime of t over phi prime of t. Formula 3. We find the values of parameter t is t first, t second, etc., tk, for which at least one of the derivative phi prime of t or c prime of t vanishes or becomes discontinuous. We shall call these values of t critical values. By formula 3, in each of the intervals t first to t second, t second to t third, etc., t k minus first to t k's, hence at each of the interval from x first to x second, from x second to x third, etc., from x k minus 1 to x k, where x i's is phi of t i's. We determine the sign of dy over dx. In this way, determining the domain of increase and decrease, they likewise enable us to determine the character of points that correspond to the values of the parameters t first, t second, etc. to the case. Next, evaluate the second derivative that equal to phi 2 prime of t times psi2 prime of t times phi prime of t minus phi2 prime of t times psi prime of t over phi prime of t cubed formula form. From this formula, determine the direction of convexity of the curve at each point. To find that asymptotes, determine those values of t upon approach to which either x or y approaches infinity, and those values of t upon approaches to which both x and y approach infinity, then carry out the investigation in the usual way. The following examples will serve to illustrate some of the peculiarities that appear when investigating curve represented parametrically. Example first. Investigate the curve given by the equation x is a times cosine cubed of t and y is a times sine cubed of t. Maybe 1 prime. Solution. The quantities x and y are defined for all values of t, but since the function of cosine cubed of t and sine cubed of t are periodic with a period 2 pi, it is sufficient to consider the variation of the parameter t in the range from 0 to 2 pi. Here the interval from minus 1 to minus a to a is the range of x. And the interval from minus a to a is the range of y. Consequently, this curve has no asymptotes. Next, we find dx over dt equals minus 3a times cosine squared of t times sine of t, and dy over dt. Oh, sorry. Okay. Equals 3a times sine squared of t times cosine of t. It may be 2 prime. These derivatives vanish as t is 0, pi over 2 pi, 3 pi over 2, and 2 pi. Okay. Evaluate. Dy over dx equals 3a sine squared of t cosine of t over minus 3a times cosine squared of t times sine of t and equals minus tangent of t 3 prime. On the basis of 2 prime and 3 prime, we complete the following table. Range of t, the first column. Corresponding range of x. Then corresponding range of y. Then sine of derivative dy over dx. And then type of variation of y is a function of x. If t from 0 to pi over 2, we have x from 0 to a and y from 0 to a. Sine minus type decreases. If t from pi over 2 to pi, x from minus a to 0, y from 0 to a. Derivative has the positive sign and our function increases. If t from pi to 3 pi over 2. X will be from 0 to minus, from minus a to 0. Okay, and y from minus a to 0 to. Negative sign decreases. And last interval from 3 pi over 2 to 2 pi. X from 0 to a, y from minus a to 0, positive sign increases. Okay. From the table, it follows that equation y prime defines two continuous functions of the type y is f of x. For t from 0 to pi, y is positive sign, see first two line on the table. For t from pi to 2 pi, y has negative sign if you see two last lines of the table. From 3 prime, it follows that limit as t approaches pi over 2 of dy over dx equals infinity, and limit as x approaches 3 pi over 2 of dy over dx equals infinity 2. At this point, the tangent to the curve is vertical. We now find dy over dt at the point t is 0 dy over dt at the point t is 2 pi is 0. At this point, the tangent to the curve is horizontal. We then find the second derivative. Equals 1 over 3a times cosine to the power of 4 of t times sine of t. Whence it follows that for t from 0 to pi, the second derivative y2 prime with respect to x greater than 0, the curve is concave. For t from pi to 2 pi, we have the second derivative with respect to f of the function y is less than 0. The curve is convex. On the basis of this investigation, we can construct a curve y o x a minus a minus a here symmetric sorry and symmetric. Okay. Maybe I give you this example in the chat, the photo of this boat. Then clean the boat and show you another example. One minute, please. Another example. Example second. Example second. Construct a curve given by the following equations. X is 318 over 1 plus t cubed, and y is 380 squared over 1 plus t cubed. It is volume of this curves. Solution. Both functions are defined for all values of t except t is minus 1. And limit as t approaches minus 1 minus 0 of x is plus infinity. Limit as t approaches minus 1 minus 0 of y is minus infinity. Limit as t approaches minus 1 plus 0 of x is minus infinity, and limit as t approaches minus 1 plus 0 of y is plus infinity. Further note that when t is 0, x is 0, y is 0. When t is plus infinity, x approaches 0, y approaches 0. When t is minus infinity, x approaches 0, y approaches 0. Find dx over dt and dy over dt. Dx over dt will be equal 6a times 1 over 2 minus t cubed over 1 plus t cubed squared. Dy over dt will be equal to 3at times 2 minus t cubed over 1 plus t cubed squared. For t we get the following critical values. T first is minus 1, t second is 0, t third is 1 over square root or cubed root of 2, and t fourth is cubed root of 2. Then we find dy over dx equals dy over dt over dx over dt. or t times 2 minus t cubed over 2 times 1 over 2 minus t cubed. On the basis of formulas 1, 2 prime, 2, 2 prime, and 3, 2 prime, we complete the following table. Range of t, corresponding range of x, corresponding range of y, sine of dy over dx, and type of variation of y. As a function of x. T from minus infinity to 1, x from maybe from 0 to plus infinity, y from minus infinity to 0, sine minus decreases, then from minus 1 to 0, here from minus infinity to 0, from 0 to plus infinity, sine minus decreases, then from 1 over cube root of 2 to cube root of 2. A times cube root of 2 to a times cube root of 4. Here, same way. Sine. Oh, I forgot from 0 to 1 over cubed root of 2. Sorry. Don't want. I cannot. Oh, I can. From 0 to 1 over cubed root of 2. Forgot. It is x from 0 to a times cube root of 4. And here from 0 to a times cube root of 2. Okay, increases. Here decreases. Then from cubed root of 2 to plus infinity. Here a from 0 to a times cubed root of 2, and here from 0 to a times cube root of 4. Okay. increases. From 3 to prime, we find dy over dx at the points t is 0, x is 0, y is 0, equals 0. dy over dx at the point t is infinity, it is x is 0, y is 0, equals infinity. Thus, the curve cut the origin twice, with the tangent parallel to the x-axis and with the tangent parallel to the y-axis. Further, dy over dx, if t equals 1 over cubed root of 2, at this point x is a times cube root of 4 and y is a times cube root of 2. Okay, and all of this equals infinity. At this point the tangent to the curve is vertical. Then dy over dx at the point t is cubed root of 2, at the point x is a times cubed root of 2 and y is a times cube root of 4. It is 0. At this point the tangent to the curve is horizontal. Let us investigate the question of the existence of an asymptote. K is limit as x approaches plus infinity of y over x equals limit as t approaches minus 1 minus 0 of 3at squared times 1 plus t cubed over 3at times 1 plus t cubed equals minus 1, and b equals limit as x approaches plus infinity of y minus kx equals limit as t approaches minus 1 plus 0 of 3at squared over 1 plus t cubed minus 1 times 3at over 1 plus t cubed equals limit as t approaches minus 1 minus 0 3at times t plus 1 over 1 plus t cubed equals minus a. Hence the straight line y is minus x minus a is an asymptote. To a branch of the curve as x approaches plus infinity. Similarly, we find same straight line, that this straight line is also an asymptote branch of the curve as x approaches minus infinity. On the basis of this investigation, we construct this curve 0 y x the graph of this curve is 0 to this, etc. At home, you must consider exercises from 1 to 54. I gave you it in the assignment. This example will be exist in our examination cards, and in these cards must be the example that we solve in our homeworks in this semester. This is our end class in this semester, and I wait you for consultation and for exam, and I wait for your writing on this lecture on the assignment, and I wait for your homeworks that you cannot send to this time. Goodbye, good luck. Bye bye.
Bye, teacher.
Goodbye.